Hi, I'm Mark Shanin from Carnegie Mellon University, and I'll be talking about diffraction line imaging. In computer vision, we use light sources as strong visual markers. Such markers can be found in motion capture suits, night scenes, and structured light 3D scanning. Now, in these applications, our goal is to find the position of these markers on the 2D camera image plane. The problem is, this task is hard to do for fast-moving objects because cameras have a limited frame rate. But, as you can see, at high frame rates, the markers occupy the image plane very sparsely. So, capturing the entire 2D image is very wasteful. So, can we design an imaging system that is more efficient for this task? Here's a radical idea. Let's save bandwidth by throwing away most of the camera pixels and only reading out the center image column. Since we're only reading out a single column, we effectively have a 1D camera, also known as a line sensor. Now, because they are one-dimensional, these sensors are much faster than standard 2D cameras. But how can we use a 1D camera to recover 2D positions? Well, the key idea is to image the scene through a diffraction grating. So what's a diffraction grating? Well, a diffraction grating is an off-the-shelf optical device that, much like a prism, disperses light into its spectral colors. Diffraction gratings are used to create artistic effects, and they're also used in many scientific applications. So, in our case, the diffraction grating disperses the light from the points, creating horizontal rainbow color streaks on the 2D sensor plane. For every point, the streak's vertical intersection with the 1D sensor corresponds to the Y position on the 2D image plane, while the point's X coordinate is now encoded by the measured color at the intersection. So let's look at an example. Here's a motion capture glove fitted with 8 white LEDs. Here are the rainbow streaks created on the sensor plane. Here is what our 1D camera measures. And here are the recovered 2D marker positions. Okay, now let's take a deeper look at how we encode position using diffraction. When an incoming beam of light enters the grating at an angle theta in, each wavelength or color exits the grating at a different angle theta out. The relationship between these angles is given by the diffraction grating equation, where d is a parameter of the grating's microstructure and lambda is the wavelength. Now, let's put a single pixel camera to capture only the light exiting at some fixed angle theta pix. Now, for our fixed angle theta pix, the diffraction grating equation gives us exactly the relationship we are looking for. Namely, for every color that we measure, what was the light's incident angle? So for example, measuring green suggests that the light entered at 47 degrees, while measuring blue suggests 54 degrees. So, to recover the horizontal coordinates, we need to take the measured color in RGB space, compute the dominant wavelength that produced this color, and then compute the incoming angle theta in, which maps to some x coordinate on the 2D image plane. Now, in practice, computing this inverse function that maps from color to horizontal position analytically is quite laborious because of a long list of other factors that we must account for. Instead, we use a learning-based approach to learn this inverse function directly. So now that we know how our system works, let's see some results. So here is a fan from before, mounted with 2 LEDs and rotating at 1000 RPM. Now, on the right, the white LEDs were captured using a 2D camera that is capturing at its maximum speed. And in green, we overlay the point position recovered using our system. Here, using our method, our system recovered the LED positions 16 times faster. We also tested our system on a motion capture suit and glove, fitted with small LED markers. And because our method does not require controlled sources, it works for light sources in the wild, like these car headlights. Okay, so now I'll mention two hardware variations that improve the performance of our system. These hardware variations aim to tackle two limitations of our 1D sensor prototype. So the first limitation is that the rainbow streaks of points that veer too much to the left or too much to the right might not intersect with the 1D sensor, and thus limit the system's field of view. And the second limitation is that our single sensor system cannot handle multiple sources that are perfectly aligned on the y-axis, because this yields a color mixture on the 1D sensor. The first hardware variation is to implement a 1D camera by defining a narrow region of interest on a regular 2D camera. The region of interest will cause the 2D camera to output only the selected columns, which will significantly speed up the frame rate. Now, the advantage of a 2D camera is that we can define multiple ROIs. And using multiple ROIs would help us catch the side streaks and thus increase the system's field of view while also keeping the frame rate high. So, here we see a system with a single ROI on the left and 3 ROIs on the right. Notice how the right system recovers points that are outside the field of view of the central ROI. So what can we do about vertically overlapping sources? Well, so far we use a diffraction grating that only creates horizontal diffraction streaks. But using a different grating, which has variation along both axes, will simultaneously produce vertical rainbow streaks as well. Now, all we need to do is to put another 1D sensor to also image the vertical diffraction, and we'll get another separate set of measurements that can compensate for vertical alignments and vice versa. So here's an example result where points are overlapping both horizontally and vertically, but combining the measurements from both diffraction sensors yields correct positions for all the points. Now, a very cool feature of our system is that it's not limited to point sources. In fact, it works for continuous curves as well. This means that we can use it for fast 3D line scanning. Here we see an object being scanned on the left, the view from the sensor plane in the middle, and the sensor line measurements on the right. And here is the recovered shape using a standard 2D camera and our result that uses a 1D sensor. Note that to the best of our knowledge, our system is the first structure light system that uses a 1D source and a 1D camera. We also built another variation of our line scanning system that is intended for scanning objects on a fast-moving conveyor belt. We tested this system by scanning the blades of a fast rotating fan, this time without the LEDs. So here we see a video from a 2D camera at 60 frames per second. Note that the camera is unable to capture the fan's fast motion, causing the fan to appear to rotate backward. And here we overlay the raw disparity measurements using our system. Once again, using line scanning, we are able to recover the disparity 30 times faster in this case. Thank you for watching a 10-minute video. We encourage you to read our full paper and we'll be happy to answer any questions that you may have in the Q&A sessions. Goodbye.